from IIT Kanpur. Then he pursued his PhD at University of Pennsylvania, USA, postdoc at Cornell University, and currently he's on the editorial board of many journals: Journal of Physical Chemistry, Biophysical Journal, and he's a fellow of Indian Academy of Sciences. He's president of Optics within Life Sciences. It's called OWLS in Germany, and he's also a president of Fluorescence Society India. Briefly, if I have to talk about, he's working, his research is mainly focused in understanding biology using light microscopes. His group is among the few in India who can make a microscope and develop spectroscopic techniques to understand biology. Currently, he's the chair of Department of Chemistry, Chemical Sciences at TIFR, Mumbai. And I'll just finish off by saying that over the years he has published many papers, and at the top he has represented Indian science at the highest level. Okay, so now with this brief, I'll just ask Professor Sudipta Maiti to give this talk, which is titled as Optical Microscopy Down to Single Molecules. Professor Maiti, for you. Please take it.
Thank you. Thank you very much, Partho. Really lovely to be in this forum. And good morning to all of you. 10 o'clock on a Saturday. It's too early for most, but thanks for being here. And I have really enjoyed my several visits to Partho's lab at IISc. This talk is online, but hopefully I will get to see you guys again sometime in the near future. And so, as Partho said, that we should build up the community of microscopists, physical microscopists in India. And I really laud this initiative that he has taken with these online lab visits, or sometimes it can be in person also. So yeah, so thank you very much, Partho, for that and for the kind introduction. So I'll talk about optical microscopy. Most of you are actually experts, but at a sort of simple level, so that I would like to keep maybe 10-15 minutes at the end for question and answer, freewheeling. You can also stop me in between. I love questions. So I'll keep it at a simple level, and you can ask me and you can go to any deeper level that you want. Okay. So optical microscopy, and the part of my work that I'll talk about today is going down to single molecules. So what actually is there? Sorry. And what do you want to see? Well, as you can see on the right, that there's a beaker of, let me just change my pointer. So you see a beaker of solution, and that's the solution of rhodamine molecule. You see the molecules on the right, the structure of the molecule, and there is a solution, and there are many such molecules, billions of these molecules of rhodamine in this solution. So the point is, there is a solution. It could be an object such as a cell, where these rhodamine molecules will be at different places. And what we would like to see is, the ultimate would be to see each of these rhodamine molecules which are fluorescent, or any other molecules which can emit light, individually, one by one. Okay, so once I can see that, that's my microscopist's job is done. There are two problems here. One is resolution. See, in this solution, you don't see individual molecules. Why? Well, we are looking at it by our eye, and there are too many molecules that are close to each other, so it looks uniform. But if I look very closely at a very small volume, there is a molecule here, there is a molecule there, there is a molecule here, and they're diffusing around. Okay? So you want to see, want to have the resolution so that I can separate out the location of one molecule compared to another. Then I will see this instead of like a homogeneous solution as little dots here and there. Okay, so that's an issue of resolution. Can I resolve down to that? Second thing is, of course, sensitivity. So sensitivity is what? And I can see this whole solution pretty clearly. And but sensitivity would be, if I even had the resolution to see single molecules at different places, would I have the ability to would there be enough signal coming from each single molecule to see? So these are the two things, the major things that we deal with in microscopy: resolution and sensitivity. So I'll tell you how we solve this. There are many ways to solve it, and some of you know, are working on different ways to solve it. Today I'll talk about mostly total internal reflection fluorescence microscope. But then if I get a little time, then I'll talk about also how atomic force microscopy can be combined with optical microscopy to give you better resolution. Okay, so we'll talk about these things we've been in the lab. Fair enough. Very good. But are you really interested in a beaker of rhodamine solution? The answer is no. We are not interested in a beaker of rhodamine solution. We're interested in something that can be biologically significant. So what is that? Well, suppose I look at molecules, and we do, and in our lab, of proteins. So proteins do a lot of work. And in fact, if you forget about the cell division, hereditary part of the stuff, then proteins pretty much do all the work in the 90% of the work in a cell. However, proteins can also go rogue sometimes. Okay, they can bunch together, form aggregates, and actually some of the most serious diseases that we are yet to solve for humanity actually arise from these proteins coming together. So what in our lab we try to do is to try to see if we can see these proteins coming together in solutions, also in biological membranes and in cells. So both all the three things we do, but we'll focus on that membrane interaction today. But let me tell you through this cartoon what we're looking. So you have proteins. Where do we go from here to here? Well, proteins are not visible typically by themselves. So you have to add a little light, little light bulb on each protein. And that little light bulb could be one fluorescent molecule. So that's why this solution could be also a protein solution, each protein having a fluorescent tag. So when these diseases happen, you have monomers going to dimers, trimers, etc., going to larger aggregates, going to even larger aggregates. Okay, so there is a series that goes on, and it has been seen, mostly agreed on, that it is something here, either very small aggregates or slightly larger aggregates, which are actually the toxic species in some of these diseases. So you hear me talk about amyloid beta protein, you hear me talk about IAPP or amylin protein, which are two of the representatives which cause two very well-known diseases: amyloid beta for Alzheimer's disease and IAPP or amylin, two names for the same thing, for type 2 diabetes. Okay, so these two you have heard of, right? Alzheimer's and type 2 diabetes. They're caused by protein aggregation. So are dozens of other diseases caused by other proteins aggregating. So we typically follow these two in the lab, and we have been able to go to a certain extent in understanding these diseases, understanding what is the basis of toxicity and which of these different species of protein aggregates is toxic by developing microscopic tools. So that's what I'll talk about today. And mostly it will be with artificial lipid bilayers, their interactions I'll show, and the cell interactions will be for some other day. Fair enough? So you're looking at single molecules, trying to develop technologies that can let you look at single molecules, but in the context of understanding protein aggregates on membranes. Let's go. So how to see a single molecule? Well, seeing a single molecule, actually, you need to do something. There are some challenges you have to solve, that of resolution and sensitivity. And let's try to understand microscopy a little bit more to see what the challenges are, how we solve. So what is a microscope? Any scope is something that lets you see something. Okay, it could be, if you remember those little slide projectors you could have that you could hold in front of your eyes and click on them. Maybe those things are gone these days, but anything is a scope which lets you see something. A microscope obviously lets you see something that is micro, that is small, too small by our eyes to see. So there is a problem of resolution. We have something very small, such as a single molecule, or even Single molecule is a nanometer, and then your eyes can only see down to about 50 micron or so. So it's a huge gap between a single molecule to very large objects in the micro world that you still can't see. You can see about, our resolution is good enough to see about the thinnest of human hair kind of resolution, which is 50 to 100. Okay, so what you do, we take objects which can emit light, let's say this arrow, and then we make an image of that which is magnified. That's what a microscope does. Takes an object, magnifies it. Okay, in this is a very 10th standard kind of ray tracing diagram, and you can see that with these two lenses, our magnification is f2, which is the focal length of this lens, somewhere up to here, and f1, which is focal length of the first lens, f1 here, and you make an image at the back of the second lens, and the image is magnified f2 over f1. You said, well, okay, all resolution problems are solved, because all I need to do is to make f2 sufficiently large compared to f1, and I have as much magnification as I want, and therefore everything should be resolved. Okay, if we want to make 100 micron, so 1 nanometer object, let's say, which is typically, let's say, a dye molecule, an organic dye molecule, a rhodamine B that we started with, you want to make 100 microns, so then that's 10 to the 5 magnification. It should be no problem. F2 over F1 inches. There is a problem. You can't do that. You know that. You can't do that because light doesn't quite go as I have drawn here. It doesn't go in these nice, neat straight lines because there is some phenomenon, some property that light has to obey, which is called diffraction. Okay. So the thing is very simple, but it's also very profound. Simple because light comes in, okay, from something, and you have to have a lens. So the lens is the device which makes an image. The lens has a finite size, and light is a wave. So whenever a wave hits some, so lens has an opening, and there's a finite size opening. And when light hits something which blocks part of it and lets in parts of it, then there is diffraction that happens. It's nothing but the fact that everywhere light goes, it actually, so we think of light going as a straight line, but it's actually light is getting emitted from any plane that you think of. You can think of light getting emitted from each small point that interferes in the far side and finally creates the bright object that you see. If you put an aperture, that is a hole, then let's say a circular aperture of a lens, you'll see that on the screen, you'll have this kind of a picture. So you can take a little point object, such as a molecule, and you put a lens, two lenses, f2 over f1, and you make an image on the other side. You amplify, magnify it as much as you want, but whatever the magnification is, you are magnifying this pattern, not a point. So if you have two molecules, this is a question, basic limit of resolution, two molecules coming close together so that their images, which look like this, are overlapping, then you cannot resolve it. That's really the fundamental problem of resolution of a microscope. Okay? A point doesn't get imaged to a point. It gets imaged to a pattern. Okay, a pattern which is something like this. If you take the intensity cut across this and plot it, it will look something like this. Okay, for those of you who know it, we have done some maths course. This is actually the square of the Bessel's function of the first one, j1x by x whole square. But anyway, that's not important. You can easily show that to be true. But the point is that a point object doesn't get imaged into a point object. Two point objects close together, their images like this will overlap and will lose a resolution. So the two molecules very close to each other, they may not be resolved. Well, what can I do with them? Well, you can make better and better lenses. Because you would say, okay, that pattern that you showed me, how big is that pattern? Can you not reduce the size of that pattern? May not be a point, but can be very, very small. Yes, but again, to a limit. That limit is given by this equation. Okay, approximately the minimum spot size you can make is 0.6 lambda. Lambda is the wavelength of the light you're using, divided by the numerical aperture, Na. This is a characteristic of the lens, very easy to understand. The lens actually, this is suppose this is a thick lens. So there are two ray diagrams here. Imagine first the blue one, and this is a thick lens which has a short focal length. The focal length is this f, and the lens has a diameter d. Then alpha is really this half angle. So you can think of this angle as the full angle, and alpha is the half angle. So the numerical aperture is sine of that angle, times the refractive index of the medium. If it's in air, then refractive index 1. So it's really sine of that angle. Okay, if it's in water, then 1.33 times the sine of that angle. Now, this angle, sine of that angle, can at best be 1. Okay, sine of any angle can at best be 1, sine 90, which should be in f is nearly 0 and d is, f over d is nearly 0. So, sine of that angle can be 1. That means you're limited in this minimum spot size to the Na is limited to roughly the refractive index. Lambda is, if you're doing visible light, let's say 500 nanometer. So this would be 0.6 times lambda, which is 500, that's 300 nanometers. The Na, if it's in air, you are limited to 300 nanometers. If you're in water, you get 1.3 33%. You get oil, you get 50%. But roughly, you are limited to a couple of hundred nanometers. So that's the problem. If two molecules in that beaker are closer than a couple hundred nanometers, even if you have all the sensitivity in the world to see them separately, they're not resolvable. All right. So, however, that's a problem which over the last 20 years or so, people have worked hard. So, to develop something called super resolution microscopy. I'll come to one version of that later in the talk, where we are doing deconvolution with an AFM. But right now, let me tell you just this. Somebody says, have broken the diffraction barrier. Technically, that is not correct. The correct thing, the light gets diffracted and you're limited by the optics. It's the spectroscopy of the molecules that we, or statistics, photon statistics, that we manipulate or that we take advantage of to go beyond the limit set by diffraction. Okay, so the light cannot be focused better than what that 0.6 lambda over n is. Okay, fair. Now, so let's actually admit, okay, fine, we can do it. What can we do then? Well, take a dilute solution, okay? Or if it's an object, solid object, and you have different objects at different distances, and you have each object, each protein molecule, for example, attached to a fluorophore, attached to a molecule which emits light, then let us take a very dilute solution. So they're separate enough. This intermolecular separation is greater than this few hundred nanometer length. Can I still see them? Yes. We do have machines, and this is a technology thing. We do have machines which are cameras and detectors which are sensitive to the light emitted by a single molecule. Okay, because a single molecule doesn't just emit one photon, it emits hundreds and thousands and typically hundreds of thousands of photons. Okay, and it can do it per second. Of course, every time it gets excited, there is a chance that it will get photo bleach. There's a chemistry. You're making something excited, it can get knocked off, some chemistry, some bond can get broken, etc. It won't be fluorescent anymore. But until it lives as the fluorescent dye molecule, it can give 100,000 photons per second. And we have detectors which can detect single photons. Okay? So detecting a single molecule is not a problem. The other thing you have to think of is a background. So of course, I cannot detect single molecule with a camera which has the sensitivity to detect single molecules, single photons. In the background of many other photons that are coming. So in my object, if I can separate the molecules that fluoresce and suppress the background photons coming from everywhere else, I should be able to see single molecules. Okay. So this is cartoon for how you see single molecules, how to suppress the background in one way. That way is total internal reflection fluorescence microscopy. So what you do is very simple. You are looking at, suppose you are interested in an object, which is a thin layer, it's a flat plane, and you're interested only in that object. You'll say, that sounds very restrictive. I want to look at everywhere, like in all parts of a cell. Yeah, but not for every problem. I told you that we are going to look at how these protein molecules which aggregate, how they interact with a lipid bilayer membrane. So a lipid bilayer membrane is nothing but the kind of stuff that you have as the cover of each cell, or inside there are organelles, things like mitochondria, endosomes, etc. They cover these. So that lipid bilayer membrane is actually locally flat, and it's especially if you talk about the plasma membrane, and it's very thin. It's about 4 or 5 nanometers thick. And if the cell is sitting on a cover slip, then you have much of the lipid bilayer membrane flat over the cover slip. So if you are interested in a protein which could be a noxious protein, a toxic protein entering the cell, it has to first interact with the lipid bilayer. And if you want to look at the first step of interaction, all you need to do is to actually visualize the lipid bilayer, which is a flat 4 nanometer thick thing, and its interaction with a protein, toxic protein, it could be a monomer, a dimer, trimer, etc., each of which is labeled with a fluorescent quantity. So this is not restricted. This is actually an advantage of looking at protein membrane interactions. If I can just see that lipid bilayer, and I want to avoid looking at everything else beyond it. I might form a lipid bilayer, let's say artificial lipid bilayer, or in cellular bilayer, and the other protein molecules, there are protein molecules coming, interacting with the bilayer, going out, or getting stuck into the bilayer. I want to look at, say, protein molecules which are interacting, getting stuck into the bilayer. I don't want to see all the protein molecules in the background. So it will be same problem as looking at that beaker, because there is huge amount of stuff, I think. So what total internal reflection fluorescence microscopy tells me is that, yes, you can do it. You can look at relatively background-free manner, look at only that lipid bilayer. Well, not quite as thin as 4 nanometers, but definitely 50, 60 nanometers. What you do is you have you take a fluorescent molecule, which means it needs to be excited. That excitation light is typically coming from a laser. You take the laser beam so that it gets total internal reflected from the glass cover slip on which your cell is, or on which your lipid bilayer is. If it gets total internal reflection, it's not like there is no, so this is the cover slip, okay, this, and this is the light field, the blue. If it gets totally internally reflected, it's not like the field is 0 right above the cover slip. That would mean there's a discontinuity in the field. No, that doesn't happen. Nature abhors discontinuities because, for many things, they will give rise to infinities. So what happens is the electric field dies slowly above this. So it doesn't propagate to a large distance. So really no light is getting lost, but the light's presence is felt right about, slightly above this layer. For about 50, 60 nanometer, that depends on this angle at which it comes in, depends on the wavelength, and depends on the refractive index difference between the glass and the, say, water that you have above. Okay, but about 60, 70 nanometer is easy. So then, even though you could have a huge amount of solution with, or a huge amount of, or a large cell, 10, 20 micron big cell, you only get to see the bottom 50, 60 nanometer and your lipid bilayer right there. Okay, so I have hopefully convinced you that this is a great way of looking at things on a flat membrane without the background. So only if we have molecules separate enough, now we have taken care of the background. I told you my detectors, my cameras, or other detectors are sensitive to single photons. I should be able to do single photon image. And you can. This is something that we built a few years ago now. Shinbi Day, one of my students, and built a total internal reflection fluorescence microscope. Why did we build it? You can buy it these days. We built it because we wanted the flexibility. We have sometimes this is hooked up to a white light laser, which is a laser which can give pretty much any wavelength in the visible light that you want, or even in the infrared. We hooked it up because we needed two cameras, okay, onto this, which are go fast but hand in hand, so that I can image something down to a very high rate, because things are dynamic. So for all these reasons, we decided that we had to build it, and we cannot just have commercially purchased things. So this is my exhortation to you guys. If all your needs are met by a commercial microscope, go ahead and buy it. Of course, if your boss has the money. If not, then frequently you can do things that nobody else or hardly anybody else can do by building your own. And that doesn't require really rocket science. You need to have some familiarity with optics, some familiarity of playing with things like these. You see an optical table, some optical things here, and then you get the components, put it exactly as you want it. Suddenly you're doing something that no commercial microscope can do. Okay, so here, for example, having these two cameras and going hand in hand, so that you can do very fast imaging together with a white light laser. All right. So do I see something? Yes, we do. On the right is an actual image. The grid lines are artificially put, so forget the grid lines. Just look at these little dots. These are actually toxic protein oligomers. Okay, they're sitting there. They are on a membrane. The membrane itself is not a fluorescent, so you don't see it, but you see the individual little dots as the molecules. Some are brighter, some are dimmer. You say, why? Every single molecule should be the same. Well, there are two very good reasons. In fact, that's why you are interested in it. One is the protein molecule can go in at different orientation into the lipid bilayer. Okay, so with respect to the light field, which has this polarization, it may or may not get excited, or may get only weakly excited. So even if all of them were just single molecules, you expect to see a distribution of brightness. That's a confusing issue, because you think that they're different species. No, they're not. They need not be. They can be, of course, but they need not. But in this particular problem, yes, they are also different species, because I have a protein solution which aggregates. There are monomers, there are dimers, there are trimers, there are tetramers, and other. And this is precisely the research question. The research question is, we have all of these oligomers. Let me give a general name, oligomers, in the solution, which means dimer, trimer, tetramer, etc., together with the monomers. Which one is the toxic? You won't believe it. This is the big question yet to be solved. We know which proteins aggregation causes which disease, but we do not know which species. Is it really the dimer, which is the smallest aggregate species, or is it really the fibrils, which are very large fiber-like species that actually cause the disease? If I knew, then I can, of course, then talk to a pharmaceutical scientist, tell him, look, this is the culprit. You take this up, build a drug or make a drug with synthetically that can interact with it and do something. You don't. So this has remained the big problem why we have not solved these diseases. Okay, so what you see here actually could also be monomers, dimers, trimers, tetramers, etc. But I told you that the confounding issue is also their orientation. So I cannot just say, okay, the brightest one must be, say, tetramer, pentamer, 10-mer, whatever. I don't even know whether it's a 5-mer or 10-mer. I have no idea, because their intensity can also vary because of their orientation. So this is the challenge we have, but this is exactly the right kind of system where you want to solve the challenge. I told you, the big challenge is to know which oligomer is toxic. So we can ask this question in a separate way. Say, I leave a lipid membrane at the bottom. I add in the solution some of my mixture, which has all these monomer, dimer, trimer, tetramer, etc., and see which one gets stuck and interacts in the membrane. Doesn't interact, is unlikely to be able to cause toxicity, right? Because it cannot even enter the cell or do something sitting in the membrane. So it has to interact with the cell. And it is possible, say if you have a mixture, only the dimers interact, or only the trimers interact, or only the tetramers interact, or a bunch of these interact, but not the monomers. But so it should be, this is a kind of a sticky paper which is catching the flies, the bad flies only. Okay, the good flies which are not toxic, they're flying around. So exactly that. I want to count how many. So I want to know. I separately know what concentration of what is there in my solution. I want to count here how many are monomer, how many are dimers, how many are trimers. I can see single molecules that, by putting rhodamine and fixing them on a surface, I already know, and I am not showing that, but I can see single molecules. But even here, there is each particle is separate enough because it's dilute that I can see them separately. But one of these particles could be a dimer. That's so close together, there's no way I can resolve them. So I can resolve separate particles, but they may be monomers, they may be dimers, they may be trimers, whatever. So there's no way I can resolve this spot into, let's say, there's a trimer. No way I can say this spot is a pentamer or hexamer, whatever. Okay. So you have to find a way to do. So this is the problem we are talking about: monomers, dimers, trimers, and hieromers. And you cannot separate. First issue is you would say, okay, why don't you separately take the dimers, look at how much they attach, separately take the trimers, look at how much they attach, and you know. This is what we do, right? We have 5 different species. One of them is toxic. You take them one by one and measure some assay for toxicity, and you'll see which one is toxic. You can't do that for this. Why can't you do that? Because there's something called, they're in dynamic equilibrium. If you just separate out the trimers, at once it will start dissociating into monomers and dimers and start aggregating into tetramers. So these species are in dynamic equilibrium. They're forming, they're dissolving, forming, they're dissolving. So you cannot separate out one of them by doing some, let's say, size exclusion chromatography, which is just like filtering, and then separately study their properties. So you have to do it together. But that's why this approach is so powerful. I'll put all of them together in dynamic equilibrium, but only watch what kind of particles attach. Maybe only monomers attach, or only dimers attach to my to the lipid bilayer that I have formed at the bottom. Okay, so let's see how we do it. But the problem remains that we don't know a single spot. Let's say one of these spots is a dimer, trimer, pentamer, one. Here we do single molecule photochemistry. Okay, there's a technique that lets you not resolve whether a spot is dimer or trimer, but by doing some photochemistry, understand, derive whether that spot was dimer or trimer. How do we do it? So each of this is an intensity trace with time. So there's intensity, there's time, and I'm looking at how much the intensity is as a function of time. I'm not doing nothing. Just take a series of images. As I said, they don't live forever, because every time you put them in the excited state, there is a possibility they'll do something. Most of the time, they do come back to the ground state, again go up and come back. So every time they come back to the ground state, they emit a photon, or most of the time they emit a photon. But sometimes they actually photo bleach, that is, they're going to a different state and they're not going to come back. And you see this photo bleaching event. Okay, so this molecule, this spot, you're following one spot, there's one spot in time, let's say this one, and suddenly it disappears, goes to the background. In one step, they say, okay, that molecule died. But wait a minute, if this spot died in one step, there must have been just one molecule there. Because I can imagine two molecules, talking to each other, saying, well, let's commit suicide together. Okay, they don't have a mind, they don't have a communication. So if you have a single spot coming down to background level, I know the background level by doing a control, then that spot must have been due to a monomer. If I have 2 steps, the spot must have been a dimer. Like that, I can just keep looking at the disappearance of this whole area and do a post-facto processing, post-acquisition processing, so that I know how many of these spots were monomers, how many are dimers, how many are tetramers, and I can plot them. And this is an actual plot from this molecule called amylin, or IAPP, let's call it IAPP, which causes type 2 diabetes in an actual experiment on a lipid bilayer. And this is the stuff we got. This is monomer, dimer, trimer, tetramer. So these are the things which actually attach. We're very happy, okay, we have solved the problem, we know what the distribution is. But then we look at it and say, that doesn't make any sense. Why doesn't it make any sense? Because monomer is the natural state of the protein. It's there in me, there in you, there in everyone. Well, everyone doesn't have the disease. It's the natural protein. It causes disease only when it aggregates. Minimum is to a dimer. So the fact that I'm saying the monomers attach a lot tells me that there's something wrong with this pattern. Most likely, it doesn't make sense. And we did separate experiments. Again, we developed these things called fluorescence correlation spectroscopy. Don't have time to talk about it today, but we knew that the fluorescence correlation spectroscopy, which doesn't have the ability to separately resolve dimer, trimer, etc., still gives an average value of things which attach. And it was saying that it would be something between dimer to tetramer, etc., some average. So that also didn't agree. Okay. Smaller than predicted by fluorescence correlation spectroscopy. Yes. So what's going on? This is where we were 2 years ago or so, and we wanted to solve it. The single molecule photobleaching technique was not invented by us. We just built it because other people have done it. But this was invented by us, where we decided that people may not be doing it correctly. Why? Because you think something is a dimer, and by the time you look at it, it may have not, because it may have been exposed to light before, or during your experiment when you're trying to find the right plane, etc., it can get photobleached. So it's called pre-bleaching. Before your measurement, it is a dimer, but one turned off. Still a dimer, but you read it as a monomer. You have to do some correction. That correction can be done if you have standards. So we made artificial standards of monomers, dimers, trimers, etc. And I knew when I have this artificial standards, they're covalently linked trimers, then they have to be, each have to be 3, yet they don't come out as 3. So you do these trimers, dimers, and monomers and look at the statistics and then impose on them the condition and derive through a set of equations how much is your pre-bleaching. Because you knew in these cases they're all trimers or all dimers or all monomers. So with that, we could do a pre-bleaching correction. With the pre-bleaching correction, then we could see that membrane affinity, that the ability of an oligomer or a monomer to attach to the membrane is actually very low for monomers. This now makes sense because all of us have monomers. The monomers hardly want to attach to the lipid bilayer. Dimers do, trimers do, tetramers also do to some extent. And they all could be responsible. So I don't have a very clear-cut answer for you that it's only the trimers and nothing else. It's definitely not the monomers, and it is somewhere around the trimers. Maybe dimers and tetramers also do that. So we are one step ahead in this. We have solved the thing that's saying that it's roughly the trimers, but probably some also dimers and tetramers, which actually are toxic species in this. And this shows our ability to separate out even hexamers and all. So we have statistics. Okay. So it's unlikely to be a single toxic species, but likely to be one of these or a group of these. So this is what the solution of one state of the problem is. I still have 25 minutes. So let me go to the higher level question in the same problem. Okay, so they are attaching. I know which ones are attaching. The next question is, where in the membrane do they go? I want to understand the interaction. Our membranes, some of you may have heard, are fluid, but also there are regions which are less fluid and regions which are more fluid. Fluid in a two-dimensional way. It's like you have a skin of the balloon, but the skin of the balloon is floppy and somewhat fluid. It's not tearing apart, but it's somewhat fluid. So if you put something on the surface of the balloon, it diffuses to other parts. They are rearranging. Okay? But parts of the balloon are rearranged less well than the others. They are stiffer, they're more ordered parts. Sometimes they're called membrane rafts. And there are parts which are more disordered where diffusion is easy. And these ordered and disordered parts have a lot to do with how cells signal, how they function, how endocytosis happens, and all of that. So there has been a lot of research on finding out whether these ordered and disordered parts of the membrane, whether they have something to do with controlling how these diseases, say IAPP, interacts with them. What we showed you before had no real resolution for that. We didn't create ordered and disordered parts of the membrane and try to see where it goes, but we can do that. So there are ways to create ordered and disordered parts. So this is my cartoon of a membrane. So these are the disordered parts. They're a little thinner and not very ordered. And these are the ordered parts. They're a little thicker. Okay. So, lipids, which make this lipid bilayer, have a tail. If the tails are disordered, the whole thing is thin. There is a bilayer. So there's a head group, tail, and then you have a bilayer. And if the tails are disordered, the whole bilayer is thinner. If the tails are ordered perfectly, okay, like stiff ordered, then the whole thing is thicker. Same lipid molecules, but regions are ordered, regions are disordered because of other molecules that are there, cholesterol, for example. There's the height difference. Now, this height difference, can I resolve it by microscope? Well, you'd say, well, we have a tough microscope which can resolve 50-60 nanometers, and if the height is more than that, then I will see only part of it, etc. I can try to do something. No, it doesn't work. I told you that the whole membrane is 4 nanometers. Your resolution of 50-60 nanometers doesn't cut it. You've got to think of something else. Okay. So these are the challenges. This is what microscopists live by. Okay, let's devise something, let's make something which can resolve this. So we decided that the technology, which is very good in measuring height, resolving height, even underwater, even in a biological system, down to much less than a nanometer. In fact, we get 1 angstrom resolution in height using an atomic force microscope. Our proteins are fluorescent. I want to see where these fluorescent spots are, but I want to see it in ordered versus disordered regions, and that I cannot see by fluorescence microscope. So I have to combine the two. The fluorescence is imaged by my fluorescence microscope, could be a tough microscope, could be a confocal microscope, and my lipid membranes are interrogated by an atomic force microscope, which is like a pin. It's like a sharp pin that comes in and feels by scanning what are the local heights, and it can go down to an angstrom or so. Even better in vacuum, but in water we get about an angstrom as the height noise, and in room temperature. So you built this optical microscope under an AFM microscope. So each has access to parts of the system. From the top, the AFM comes. From the bottom, you have this fluorescence microscope, and you combine the 2 images. The top is making an image of a height, and this is here. Okay, the lighter sort of yellow parts are the taller parts, and this line is a height profile. You see the height. This is exactly this line. This is where it is. The heights are occasionally high. These are the ordered regions. These are the ordered regions. This, and that. And intermediate, these regions, darker orange, are the disordered regions where the height is low. And the difference of the height, this is in nanometer, you'd see is about 1 nanometer or so. Okay, which is good enough because you'd see our height noise is about an angstrom. So we can resolve the height difference of a nanometer very easy. No problem. Okay, with the AFM. Same bilayer. We are looking at it from the bottom because we have now built a microscope or fluorescence microscope from the bottom. It gives you an image like this. And what is fluorescent here? What is green? The green is actually labeled IAPP molecules, which you see if you correspond with this. You see the edges are not very sharp. Here the edges are sharp, but of course you have outlined it. But if you look, it cannot tell whether this height and this height is different. It seems like it's choosing the disordered domains. And I know from the AFM that yes, this is the ordered domain, this is the disordered domain. So I can match these two. And in fact, I can overlap them. Okay, overlap them and put brighter regions in green, darker regions in red, and this dark red, orange and green tells me that most of my IAPP molecules are going into the disordered regions. So we know that those rafts that people talk about, do they have a role to play? Potentially, yes. They do have a role to play potentially because they do prefer the disordered regions over the ordered regions. Okay, so this is one more set of information now we have about the disease. which I had to obtain by putting these two microscopes together. I want to go further. Okay, if I come back here, I want to know how are the edges. The edges are interesting places because if you have an ordered region and a disordered region, they can remodel. In a living cell, they're remodeling. That is, the ordered region either is shrinking or growing, depending on many factors. And this remodeling is essential for the cell to function well. Okay? So we wanted to know if these edges of the things are somehow stabilized. Somehow this ordered domain is so stable that some other agents which needs to remodel it cannot do it, or maybe it enhances it. We didn't have it. We had a hypothesis it cannot do it, but we needed to look at the edges. The edges are too sharp for optical microscopy. So what do? You actually have an AFM image, and you know, compared to this AFM image is very sharp because you can have a tip. So use typically soft tips because we don't want to puncture the soft membranes, but they're 20 nanometers. So it's much, 10 times better than optical resolution. And we know how big the optical spot, the resolution would look like in the same scale. Okay, this is the scale. So that's too big compared to the edges. If you see, the edges are sharply defined. But I know the spot size. This is called a point spread function, which is the measure of how sharp your optical image is. And I can convolute these and deconvolute the image, the optical image, using this, deconvolute. It's a series of procedures to just see what is there at the edges, whether the edges stand out in the fluorescence microscope. So normally the edges may stand out, but I don't have the resolution to see if they stand out. This is the first pass. This is the second pass. Finally, we have, you see this little edges. These are the boundaries, same boundaries that you see here. The boundaries are lighting up, which means that we have, with this increased resolution, the increased resolution is shown here. There is a cut through the optical thing. The optical resolution is this much, the black line. And this deconvolved resolution is this one. Now I have optical resolution using separate information from AFM, which is much below the diffraction limit. Okay, I can go further below if you allow me to damage the membrane, but this is good enough. This is about 70, 80 nanometers. That's the resolution we have. That's good enough to tell that most of my IAPP molecules are at the edges of the domain. Okay, so you have different areas, ordered, disordered, they are mostly at the edges. Mostly means 30, 40, 70% more likely to be at the edges than in the middle. Okay, what are they doing there? This is a very interesting observation. Question is, are they doing something by going to the edges? When something in a chemical system localizes somewhere, usually it's stabilizing because that's a lower energy content. And yes, they're doing it. So now we ask, can the membrane be easily remodeled, or is it inhibited by this IAPP oligomers? So here you see an AFM image, okay? And again, the lighter yellow is the ordered domain, and the darker brown is the disordered domain. And we can make the disordered domains more likely, or ordered domains disappear by removing cholesterol. Okay, methyl beta cyclodextrin is a molecule that removes cholesterol, and I can introduce it, and you can slowly see the ordered domains disappear. Okay, this 10 minutes and then 80 minutes. So you see the ordered domain, same thing. This guy is here, disappear. You do the same experiment just with 100 nanomolar IAPP. You see time 10 minutes, 10 minutes. And you see even 120 minutes, okay, 80 minutes somewhere, times, okay, let's say 22 minutes, 24 minutes. They stabilize the ordered domains. What do we learn from them? We learned that IAPP may interact with cell membranes. This is, of course, artificial lipid bilayer, so I can only hypothesize that this similar thing happens in a living cell, that they stabilize the rafts, which is also a bad thing because you need to remodel the ordered domains dynamically. And this is somehow hampering the cell's ability to remodel the regions that needs to be remodeled. There is another piece in the basket or in the puzzle that solves why are these oligomers toxic. But as I said, they don't know. Which oligomer is toxic, we didn't know. Now I'm talking about dimers, mostly tetramers, but dimers, mostly trimers, dimers to tetramers included. And now I'm saying one of the possible reasons is that it goes as at the edges and it stabilizes the phase separation in the middle. Now the third question. The third question, and this will be probably my last question, we asked, okay, now we looked at it in sort of a two-dimensional manner. This is where my molecules are, this is not where they are, and they are also more in the edges than in the middle. Fair enough. Do they insert? Do they go in and do something? How are they stabilizing the phases? How are they interacting with the membranes? There's a theory that they go in and make pores, holes in the membrane. And these holes in the membrane can also be something that is toxic. So therefore, I wanted to know how you can tell if something is inserted deep in the membrane or hanging around on the surface. This is again, I'm talking about in a 4 nanometer object, are they near the top, near the middle, near the bottom, where they are? Okay, very tough to tell. Because that depth, I can't do it by AFM because it doesn't feel, it feels the whole membrane. It doesn't feel some protein molecule which is below the membrane, inside the membrane. So AFM can't do it. And as I told you, this is even sub-nanometer resolution that they need. There is no way optical microscopy is going to happen. So Arpan from our lab did this, came out with this idea that we can try putting something in the solution which will be in the solution, not get into the membrane, and so much at least, and check if that particle is changing the fluorescence of this fluorophore. If it changes, that means that fluorophore is exposed to the solution. If it doesn't change, the fluorophore is inside the membrane. Okay. How does it change it? Well, it's something that quenches. Okay. That's something that quenches could be in, okay. So that's one thing. You can tell whether it's exposed to the solution or not. I want a final question. Where is it in the membrane? Is it near the top part of the membrane, middle of the membrane, bottom part of the membrane? Where is it? Well, there are other quenchers which can be labeled. They're not soluble quenchers on the lipids. So on the lipid, I have separate quenchers, and these quenchers can then also quench. What do you see? Single molecule photobleaching, if you quench fluorescence, well, you say they get less bright. Fair enough. What happens when they get less bright? Why are they getting less bright? They get less bright because they go to the excited state, they quickly come back. Remember how photobleaching happens? They hang around in the excited state, sometimes in the excited state called S0, sometimes in the excited state called E1, the triplet state, etc. And they die from there. It's like you go on top of the mountain and these guys commit suicide by jumping from there. Or they can come down the stairs and go to the bottom again. So the point is, if something just gets them down by an elevator quickly to the ground state, then they do not forget photobleach so easily. So if I'm looking at a protein molecule, one single molecule, the length of time it will take to photobleach increases. Okay, so it's called Q-SNP is what we called it. So which is quenching induced step length increase in photobleach. Is another method there, yes, we have come up with, which tells you how exposed is your molecule to that quencher. Is it close to the elevator that you can go down, or is it far from the elevator? And I know the location of the elevator because I have put those elevators, quote unquote, the quencher molecules, in particular depths in the membrane by attaching them to the lipid molecules. Okay, they are called radicals. Doxin is a radical. I know at different depths I put in, I measure whether the step length increases or not. If it doesn't increase or doesn't change, that means it's far from that position. If it increases, that means it's close to that position. So this is the experiment. Okay, I put a fluorophore. This is my protein. Okay, just think about one monomer, then but oligomers is just 2 or 3 of those. You have quenchers called tempo and the head group. This is the lipid bilayer. Okay, so this is the head group. This is the 2 tails. This is the other side head group, 2 tails, and you can put it on the head group. You can put it right below the head at 5' position, sort of halfway below the head, 10 prime, or near absolutely the middle, that is tail of the lipid, each lipid at 60. And you can ask, does my step length increase here, 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 or here? Okay, wherever the step length increases, it's an indication that your fluorophore, which is stuck to one part of the protein, I can put it anywhere else, say the C terminal, and I will know where exactly is in the membrane, where that protein is in the membrane. Okay, these are the lipid molecules. This is a doxil quencher at different places on the lipid. Okay, this is what happens. You can put control, no doxil, 5 prime, 16 prime, and you can see how things change. Okay, and that change tells you where which object is. Remember, this is still single molecule photo bleaching, so I know whether that object was a monomer or a dimer, a tetramer, or what it is. And this is the plot that Orphan got. So just compare monomers versus tetramers, the differences start. Look at this. So when we have it in the 5 prime, there is a step length change. So 5 prime is just below the head. So most of my fluorophores, the end termini of the IAPP are located there. If I look at this 16 prime, deep inside, they hardly go there. So there is a difference between control. So I know that some of them are getting to, many of them are going to the 5 prime, but hardly anything is, this is not significant. So hardly anything is going like this. Come here, tetramer. Look at this. This is the 16 prime. The tetramer is very different in its way of inserting into the binding. The lot of the tetramer, lot of fraction of the tetramer is at 16 prime position, this purple thing. So this and this is statistically very significant. In fact, this and this is very small, difference is small. So compared to the monomer, I know that the tetramer inserts much deeper. So this tells you that when I have a seemingly insurmountable challenge of having to tell where exactly my protein is in a bilayer with sub-nanometer accuracy, if you think of it right, if you apply your microscopy tools, you can still correctly solve it. Okay, so we know why. So the question is, why are dimers, trimers, and tetramers more toxic? Well, they do, possibly because they do insert deeper into the membrane. So the whole story puzzles coming together. That's where I will end. I have now 5 minutes only left. Okay, so this is what I told you. First is, was there a question?
Okay. No, continue, please.
Okay. So first is that why are monomers not toxic? Because all of us have them, but oligomers are toxic because the attachment to the lipid bilayer is much more for the small molecules. How did I get it? I did it by making single molecule imaging device and employing single molecule photo bleaching with the correction factor that we developed. Then I told you that do rafts matter? Yes, they seem to matter because the attachment depends on the local membrane order. Ordered regions do not take up as much as the disordered regions. For this, I had to develop some combination of atomic force microscopy and fluorescence. I can put these two together to increase the resolution of fluorescence microscopy by doing something called deconvolution, and the oligomers seem to go to the edges of the domains and they stabilize them. So the remodeling of the membrane is hampered, and this is something that physiologically is necessary, hampered when you have these molecules, even at 100 nanomolar, very small concentrations. Okay. Then I said, well, that's about the distribution in a sort of lateral direction. Why, coming back here, why are possibly tetramers, trimers more toxic than the monomers when the monomers little bit, still interact? Well, and do they have a difference between dimers, trimers, tetramers? So I showed that there's a method that we have developed called Q-slip, which can measure the degree of insertion of individual oligomers. Okay. The monomers and tetramers, monomers hardly interact, but whenever they interact, the monomers are also. So what I showed you that monomers are hardly ever interact with the membrane, that was a relative thing. But if you have huge concentration of monomers, then a small probability still means a large number of monomers do interact. But when they interact, they are actually very different in their insertion from tetramers. So this sort of gives you an idea as much as possible from microscopy and artificial systems, why small oligomers are much more toxic than monomers, and how are they becoming more toxic? A, by inserting deeper, and B, by stabilizing the membrane domains. Okay, so that's all I have, and I have to thank the people who really have done all the work. So much of the work is by these three. Ankur Gupta, who just left for a postdoc a few months ago, and he did all this AFM kind of experiments, helped very well by Dev Shankar Saharai. They did this deconvolution thing together, and then much of the single molecule photo-bleaching stuff was done by this guy, Orpan Dey. Okay, of course, we have a small lab, but the rest of everybody helps. And Orpan's methods just got published as a chapter in a book. So if you want to read it like from the basics, the papers typically won't have that much detail. If you really want to know about that, this is the book that you want to look at. I didn't talk about FCS, but I typically get asked a lot of questions on FCS. So FCS also now we have a book, so you can look at these. The funding, of course, the collaborators is very important. Daniel Huster has been a major collaborator for us. Daniel was actually here till yesterday in a short 2-week visit and just left. And we collaborate very strongly together. Some of my students have been there, I go there, etc. So thanks to him. And funding comes from the Department of Atomic Energy through the IFR, also from Department of. Thank you very much, and I'm open to questions.
Thank you, Professor Maiti. Indeed, a very absorbing talk and a great insight in disease biology. This goes down as one of the finest talks that combines fundamentals of optics and advanced microscopy for applications in disease biology. And, great to see that some of the sophisticated home-built setups based on the need during the investigation, and which is quite rare in India. I would like now, if someone has some of the questions, we can ask some questions. Yeah, please.
One participant asked a question in the Zoom chat. Can I read it?
Hello. Also, thank you so much for the really nice talk. So I had a question. So using these fluorescent microscopy tools, is it possible to quantify the concentration of toxic molecules, like, say, for example, lipids or glucose metabolism-based disorders for early disease diagnosis?
Yeah, absolutely. So, see, you'll have to find a model where, so most of us do fluorescence microscopy, most of the things that you see. So if you have a disease model where fluorescence changes in some way, or fluorescent reporter can be attached to an agent which is a toxic agent, then I think fluorescence microscopy would be one of the best tools to look at it. You can look at it, as I described, on a flat lipid bilayer. If bilayer interaction, membrane interaction is important, or you can look at cells, not with TURF, but with other fluorescence techniques, and you can look at it. We are doing it. So some of Orpan's other work, for which he's actually doing some biological stuff, we will be in Bangalore next month, in 2 weeks actually, or 3 weeks, is done in cells. And there we have put together something called a multiphoton microscope and a single photon spectral microscope together. So that Dev Shankar has built, and we do the lifetime apparatus that we have built. So with different kinds, optical microscopy really has, you have to remember, it has many parameters to play with. So what I showed today is intensity and drop in intensity with time. That's just one parameter. You can do spectrum, you can do lifetime, you can look at diffusion, look at change of location, you can do polarization, anisotropy. You can actually take care of all the properties that the photon has and do different kinds of interrogation. So only point is that your molecule or something in your system has to be fluorescent, whose change either in location, rotation, orientation, or fluctuations has to respond to the parameter you're measuring, such as something to do with this. Yes.
Okay. Any more? We have a few more.
So thank you for your talk, sir. It was great talk. So can this technique be used for finding the antimicrobial action of some unknown phytochemicals in bacteria?
antimicrobial actions of some unknown phytochemicals in bacteria. Okay, so see, you will have to have again a hypothesis in mind, and then you can test the hypothesis by devising a strategy which is dependent on fluorescence microscopy. I'll tell you about one that we are working on right now that I didn't talk about at all. So we are attacking one particular protein on a gram-negative bacteria. So we have developed some agents using some principle that we have developed in the lab, and they seem to be acting on the bacteria in the sense they're becoming toxic. Thing to know is that whether this agent interacts with this particular protein. So for that, what we can do, we haven't done it yet. My other student, Anup, is trying to do it. You have to have one label on the agent and one label on the protein. And if they interact with each other, you can do something called FRET microscopy, Forster resonance energy transfer, okay, microscopy, and you can do. But that can also be done with a TURF. So good thing about fluorescence microscopy, once you build one microscope, it's like learning how to program in one language. Once you learn how to program in C and somebody says Python, you just have to read it up and the basic grammar things remains the same. You can easily adopt it. So you try to translate your problem into something that can be sensed by fluorescence, and you'll have a way to do that. No problem.
Thank you.
Anyone else?
Hello, sir. Can these techniques be used at the subatomic level?
Subatomic level. Okay, that's a new one that I haven't thought about. See, fluorescence can come from atoms. Okay, so but usually atomic fluorescence is at a very high energy.
Okay.
So people do atomic fluorescence, but typically not in the context of biological things, unless they're ready to destroy the living thing, because you'll have to put in deep UV light in order to excite the core photons to look at subatomic things, because your dimensions are of that order. People do things such as microscopy, which is mass imaging, which is spatially limited, not using fluorescence. So the fluorescence we typically use are fluorescence of organic dye molecules or of proteins such as GFP, which are much bigger than the subatomic scale.
So one more doubt. These techniques are performed lively in the labs or something. Can these techniques be used in the digital twin and simulating it digitally and finding it?
Okay. So, of course, this is a very good question. So, all of us need to be very, very aware of the technological progress that's happening on the computation side, especially with the machine learning part that is coming up. And we do have plans where we want to, for example, looking at these little jumps in fluorescence. And nowadays, there should be, and we are developing it together with a group in Monash, ways to properly, quickly count these steps, even from noisy data with reliability. So that's kind of a digital approach to experimental data. Ultimately, you'll have to do some experiments because simulating the whole cell is very, very far away. But the experimental data, hand in hand with digital, such as machine learning approaches, I think have a great future. And in fact, we are doing some of that. Just began to do some of that. If that was your question, does that answer the question?
Yeah, thank you. And there are some more questions online. I will just quickly go through.
Okay.
So someone asked, sir, why do we say that it is single molecule? How do we confirm that it is single molecule and not a clump of single molecule?
Good. Very good question. And think back to the slide where I showed jumps in fluorescence. So as I said, suppose it is two molecules together. Then if I wait long enough, I should be able to see two jumps. As I said, molecules don't have minds, so they cannot shake hands, let's say, let's jump together. That hardly ever happens. So if you look at a spot and you see single steps, that must be coming from single molecules. Of course, two molecules can be together. That's how it's a problem. Are they dimers or monomers or trimers? The point is, if they are monomers, they'll have one jump, and that's a single molecule. Or if they're dimers, I'll have two jumps sometimes, and they'll be dimers. But you can see that whenever you see monomers, you do have the sensitivity to see single molecules.
Okay, thank you. There is another question. Can the graph shown to prove that molecules are monomers, dimers, etc. is because of quenching as shown in slide number 21 Q slip?
Okay, let me quickly go to the slide 21 here. Okay, so yeah, so the question again is, can this be, sorry, can you read the question again? Sorry, Pastor.
So can the graph show to prove that molecules are monomers, dimers, etc. is because of quenching as shown in the slide number?
Okay, so the quenching and the bleaching are two different things. So it's a great question, and I should have explained it better. Quenching means every time that the molecule gets excited, there is a higher probability now to come back to the ground state. It's not bleaching. It can go up again and come back again. But it makes the molecule less bright. Overall, all of the, any molecule that is interacting with the quench. Bleaching is when it comes down and it's actually reached a different ground state, which is not fluorescent. It has become essentially a different molecule. So what quenching does is that this part of the step, this part, becomes less bright. And bleaching is this part. Point is, when this becomes less bright, that means it's reaching the ground state more efficiently and its length of life increases. So step length increases. So length of life is when it takes the step again. So whether it's a monomer, dimer, trimer is still told by these steps. This step, and this step. So this is a trimer. Whether it is getting quenched or not is told by this thing increasing. So this thing increases to that. I know that this actually is getting quenched.
Thank you, Professor Maiti. I do have a question. I thought I'll ask. So, does the presence of dimers, monomers, and trimers and other mers basically has some implication in disease biology?
Right. So,
does it show disease progression or something similar to that?
So that's a fantastic question. So actually, what is the bigger question in all of this is, can we tell somehow whether the monomers or dimers or trimers or tetramers, which of these is more associated with toxicity? So for toxicity, we do not know the mechanism. If we knew the mechanism, we can have an assay for the mechanism and ask, is the dimer doing it better than trimer or trimer doing it better than tetramer, whatever. We don't have a mechanism suggested. However, most people agree that it has got something to do with how they interact with the membrane. So we have taken 3 features of that membrane interaction, tried to see whether the dimer, tetramer, or whatever does it better or worse. So one feature is their attachment. One feature is their preference of domains and stabilization of the domains. And the third feature is their insertion. So if I can put this together and prove that these actually have a direct relevance to the disease, then I have a measure for disease progression. Suppose only the trimers do it only when they are attaching to the edges. So then I can take cells from actually patients, and these are pancreatic islet cells, or I can take blood cells and differentiate them into these islet cells and try to test possible pharmaceuticals against them. So we are not there yet, but we are trying to pose findings saying how do they fit in this puzzle of why do they become toxic. If we have all pieces of the puzzle, why they are toxic, that's the step that you can follow with for disease progression or for disease intervention, basically as an assay for developing a drug.
Okay, I think we have a lot of questions. So finally, I would like to thank you for the absorbing talk, and what a enlightenment. I think it's really a talk that shows how microscopy can help in disease biology. Thank you, Professor Maiti, for taking your
You're
time
most
out.
welcome. Thank you for giving me this chance to interact with your lab and others. So I'll see you, Partho, sometime.
Yeah. Thank you. Thanks a lot.
All right. Bye.